Alright, so let's compute some partial derivatives. And basically all we're doing here is applying a theorem that we talked about earlier in the section. So if we have capital F, lowercase f, and gi rn to r, and f of x is f of g1 of x through gm of x, then di f evaluated at a equals the sum from j equals 1 to m of dj f at g1 of a through gm of a times di gj of a. So what happens is, the sum j, j ranges over the number of j ranges over the dimension of the domain of f, and this holds for every single I, and so I is going to be any number. It could be between 1 and n, I believe. Correct. Yes. Alright, so let's apply this. Basically, once you get a feel for how this works, it's not too difficult. So here we have f of xy equals this whole thing. So what we're going to do is we start, and there was an example problem earlier on in the section, and that sort of shows us how to do it. So let A be the point gx ky, gx plus h of y. So then d1 f, well, this is a function of xy, and this is going to be, we first take d1 and evaluate it at f of all of the functions on the inside of lowercase f, but that's just f of a, times, now we take d1 applied to this first function on the inside of a. So this is going to be g of x times k of y plus d2 fa times d1 g of x plus h of y. So it's d1 applied to g plus h. Okay, so now we can d1 of, well, we don't know what lowercase f is, so d1 of f evaluated at a, there's no way for us to compute that. Without, we would need more information to do that. But we can take the derivative, we can take d1 of g of x k of y, because the 1, this refers to just the first variable, which in this case is x. So g of x, we take the derivative, that's just going to be g prime of x. And then k of y, well, that's just a constant. So that just stays the same. And then we add d2 f of a times, now if we take d1 of this, well, we take the derivative of g of x and we get g prime of x. But if we take the derivative of h of y, well, that doesn't depend on x. So it becomes 0. Okay? So that's all we do for d1 of f. for d2 of f, it's going to be similar. We start with d1 of f of a times, now we have d2 g of x k of y plus d2 f of a times d2 again g of x plus h of y. So this is going to be d1 f of a, and this time g of x stays because it's a constant and it's being multiplied by k prime of y. And then we add d2 of f of a times, and now the g of x drops off, and so we just have h prime of y. Okay, so there we go. And that's part A. So that's a general idea on how we do these. Now, go on to B. So we have f of x, y, z. So we have 3 input variables, and so we can compute d1f, d2f, and d3f. And those will be the derivatives with respect to x, y, and z, respectively. So this is f of g of x plus y, h of y plus z. And then we let a be whatever we're plugging into f. So it's g of x plus y and h of y plus z. This will just make everything easier to write. And then we have d1f of x, y, z. So this is going to be d1fa times d1. And now the first thing we have is g of x plus y. So it's d1 being applied to g of x plus y. Plus, now we have d2 f of a times d1 h of y plus z. And so the first term, we're going to have d1 f of a times, and then we just use the chain rule. Well, I guess you're technically using the chain rule, but it's just going to be g prime of x plus y. By the chain rule, you technically have to multiply by the derivative of the inside, but the derivative of the inside is just 1, so you're good. You always have to be careful whenever you have something on the inside that's not exactly just the variable with respect to which you're taking the derivative, but here it turns out to be fine. All right, what else do we got? Well, the other term, we're taking the derivative with respect to x of h of y plus z. That doesn't depend on x, so that's 0, and so it drops out. So this is all we have. So now d2 of f, x, y, z. This is going to be d1 f of a times d2, correct, g of x plus y plus d2 f of a times d2 h of y plus z. And so now both terms are actually going to stay. So we have d1 f of a times, and now we have d2 of g of x plus y. That's again just going to become this. Now we have d2 f of a times, and we got h prime of y plus z. Again, same idea. Then finally we move on to C. Nope. Not there yet. We move on to 3 because f has 3 inputs, so we can take the derivative with respect to z as well. d1 fa times d3 gx plus y, that's going to drop out. Yeah. And then we're adding d2 fa times d3 of h y plus z. Second one will remain, and we'll get d2fa times h prime of y plus z, because there's a z dependence, and we're done. So now I can move on to C. Alright, so we're going to let f of x, y, z, so again we have to do 3 things instead of just 2, so that's a little tedious. Now we actually have to do a little work. So f So it's going to be x to the y, y to the z, z to the x. We have a is going to be, again, just the input, x to the y to the z, z to the x. Now we start with d1, f of x, y, z. So we're going to get d1, f of a, times d1, x to the y, plus d. You know what? Let's not do this in two steps. We can do this in our heads. So we're going to multiply by the derivative with respect to x of x to the y. And so assuming that y is not 0, we'll just get... Why is my alarm going off? Oh, because I'm cooking something. Well, anyways. So don't worry, it'll be fine. So y x to the y minus 1, assuming that y is fine and everything. Okay, so we get that. And then we're going to get d2 f of a times, now we're going to take the derivative with respect to x of y to the z, but that'll drop out. And so then the last term will involve the derivative with respect to x of z to the x, so that won't be 0. So we can go ahead and write this term out. So we get d3 fa times the derivative with respect to x of z to the x. So assuming that z isn't 0 or anything, we're going to get z to the x natural log of z. Also assuming z isn't negative. Well, if it is negative, I think there's something you can do using complex numbers or something. I don't know. Don't worry about it. Just assume everything works nicely. Okay, now d2f x, y, z equals x to the y. That depends on y, so we'll get we always start at d1 f of a times derivative with respect to y of x to the y. That's going to be x to the y times natural log of x, just like before with x to the z. And now y to the z, that will again depend on y, so we get d2 f of a times derivative with respect to y of y to the z, which is zy to the z minus 1, again assuming everything's fine. Then the last term will be we'll have derivative with respect to x of y of z to the x. That'll drop out, so we don't include that. Alright, and so now the last one. X to the y, that doesn't depend on z, we ignore it. So now d2 fa times derivative with respect to z of y to the z. That'll be y to the z natural log y plus d3 f of a. This term will obviously be involved xz to the x minus 1, and we're good to go. Okay. By the way, I'm a little hesitant to say obviously because I just noticed a video that I did in a previous Spivak exercise where I said, no, it was actually a baby Rudin exercise. And I said, obviously this is true. Turns out it wasn't true. Although also it turns out that the thing that I said was not in any way related to or needed for the proof. So I could just delete that false statement and the proof still held. But still, you don't want to see that happen. Anyways, so here we have capital F of xy, so we have both d1f and d2f, but we're going to have three terms involved. So d1 of f xy equals... Okay, so every single term depends on x, and so we're definitely going to need to write out every term. So we have d1 f of a times d1 x. Well, the derivative with respect to x of x is 1, so we just leave this here. Plus d2 f of a times the derivative with respect to x of g of x, so that's just going to be g prime of x, plus d3 f of a times, now we have d1 of h of x comma y. And that's really all we can write here. Because h is a function of both x and y, and so we don't really have information about what this derivative is going to look like. All we can do is just leave it at d1 of h of x comma y. All right, and so yeah, that is actually a little tricky. And one of the trickier and more subtle things about this is when do you have something that you can actually like continue to write the derivative in a different way, and when do you have to stop? And it takes a little getting used to. But yeah, here there's really nothing you can do here, and so we stop. Whereas if you have, like, if you're taking the derivative with respect to x of g of x, then since this is a function of only the variable x, you can immediately jump to, okay, well, whatever this is g prime of x. Although I guess that's technically the exact same thing as d1 of g of x. So yeah, it gets a little confusing, but you get used to it. All right, and then finally we have d2 of f of xy equals, we don't have to write the first term, we don't have to write the second term, and we only have to write the third term. So we jump all the way to d3 of f of a times d2, because this is that's the derivative we're taking, of h of xy again. So yeah, this is basically just an exercise in making sure that you know how to take partial derivatives, and more specifically, making sure that you know the rules for that one theorem that appeared earlier in this section. And once you understand that, then you can do the rest of this exercise, and you can do a bunch of derivatives like this. So with that, we're done.